Okay, so let's do like a mini proof. We're going to fill in the blanks. So if you take a look at number 1, all the way in step 5, we want to prove that triangle ADC is congruent to triangle BDC. And we do that by using one of the 5 methods that we talked about in class. Okay, so let's take a look at what's given to us. So the first step says that CA, we're going to mark it in the diagram, is congruent to CB. That is given. Step number 2, we know that D is a midpoint. That's also given to us. Well, what can we get from that? If D is in the middle of segment AB, that means it's breaking this segment up into 2 congruent parts, which we can mark on the diagram, but we also have to write out in our proof. So I'm going to say that AD is congruent to, now the order of the letters is important. Based off of what's labeled right now in the diagram, I see that this is going to have to be a reflection. So if I said AD, well, A reflects to B, and then D would stay where it is. So AD is congruent to BD. How did we know that? We knew that from step 2 because we know that D is a midpoint. So the definition of a midpoint is that it breaks the segment into 2 congruent parts. So we're going to say definition of a midpoint. Okay. Now what else can we get here? We can't just put in whatever we want. There has to be a reason behind it, a theorem behind it. We've used up the givens. Well, something we talked about in the previous lesson is if 2 triangles share a common side, we can use the reflexive property. We can put an X over it, and we can say in step 4 that CD from the left triangle is congruent to CD in the right triangle. Reflexive property. This will come up in a lot of proofs that we're going to do. So if you need one more congruent part, you have 2. But you need a 3rd congruent part in order to prove the triangles are congruent. Sometimes reflexive property will work for you. And then in step 5, why are the 2 triangles congruent? Well, we look at the markings. Take a look at one triangle. It doesn't matter which one. I'll look at the one on the left. And look at what's marked. Side, side, side. We have 3 pairs of corresponding sides that are congruent. So this is a completed proof. Number 2 asks us to describe the single rigid motion that maps triangle ADC onto BDC. Well, we already talked about how, based off of the markings, it's going to have to be folded over. It's going to have to be a reflection. But it says to describe the rigid motion, so we have to give a little bit more information. Well, it's a reflection over segment CD. Okay, let's try another one here. Okay, so in number 3, let's look at all the way down step 5. We want to prove the triangle ACE is congruent to BDE. So we're going to go back up and use our givens first. The first given says angle ACE, mark that in, is congruent to angle BDE. Okay. Next step, second given, says that AB bisects CD. Bisector, we're cutting something in half. What are we cutting in half? Look at the end. We're cutting CD in half. So mark in the diagram, if CD is being cut in half, that those 2 segments are congruent to each other, because really E turns out to be a midpoint then. But don't just put in the diagram. We have to mark it in, or write out in our proof also. So we have CE is congruent to, now we have to tell what kind of rigid motion it is. Well, because of the markings, I know that this is going to have to be a rotation. That's the only way that angle C would map onto angle D is if you rotate. So C, after the rotation, would map to D, and then E would stay E. So it's CE is congruent to DE. How do we know that? Because in step 2, we know that we have a bisector. It's the definition of a bisector, which we have used in class before. So maybe you even knew that. So make sure with everything you're writing it in the proof, you're also marking it in the diagram. Now we need one more congruent part. We only have 2. We need a 3rd one to see if it's, you know, side, 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 say a side, angle, side, and so on. Well, this is one that we have used a lot this year. If you notice, the angles across from each other here are vertical angles, 2 angles across from each other. And instead of writing out the 3 letters, okay, and then doing the rotation in your mind, what you can do is just give them numbers. It'll make it a little bit easier, especially because proofs involve so much writing. So a lot of times when you add in a step with angles, I'll just change it to numbers. So we have angle 1 is congruent to angle 2. And just like we used to write back in the beginning of the year, that's because of the vertical angles theorem. So the vertical angles, you're not going to have a given. You're going to just have to look at the diagram, and you're going to have to recognize, hey, those are 2 angles across from each other. Those are vertical. So now why are the triangles congruent? Okay, cover up one triangle. Let's take a look at the one on the left. Remember, when you go around in a circle, you can only skip one thing. So if I start with angle C, I'm going to have to go around this way, clockwise. Angle, side, angle. Just look at one triangle when you do it. Angle, side, angle, looking at your markings. And the next question says to describe a single rigid motion that maps ACE onto BDE. Well, we know it's going to have to be a rotation. Okay, that's the only way you can get angle C and D to be congruent. It's going to have to be a rotation of 180 about point E. Rotation of 180 about point E. Okay. And let's just try, I think one more is all we have to do here, and then we'll be good. The next one, okay, we have to prove the triangle IJH congruent to triangle LJK. Let's go back up to the given, see how we're going to do that. We have that IL and HK bisect each other. We've talked about this before with the diagonals of parallelogram, of a rectangle, of a rhombus, and of a square. The diagonals bisect each other, cutting each other in half, right? So just like we used to do with the quadrilaterals, we're going to mark in, hey, these two segments are congruent, cut in half, and the other two are congruent to each other, cut in half. Bisect each other is the only time you can do both pairs. So really J turns out to be a midpoint. Okay, so let's mark it in the diagram, but also write it in the proof. So we have HJ is congruent to, okay, now this is going to have to be a rotation here because of the mapping with those sides being congruent. So H would rotate to K, and J would just be J. Now, I put both of the bisector congruent parts in the same step because it's the same reason. So that's how I have this, set up here with 4 steps. If you put them separate, you're going to have a 5-step proof. Okay. Other part was IJ is congruent to LJ. And all of this is because definition of a bisector from step 1. You go back to the given. What did the given say? The given said bisector, so definition of a bisector. Okay, we need one more congruent part. We just did it in the last problem too. We have vertical angles across from each other. Angle 1 congruent to angle 2. Vertical angles theorem. Now we have our 3 congruent parts. We can figure out why the triangles are congruent. Make sure you look at one triangle when you do it. Side, angle, side, right in order. 2 sides with the included angle, side, angle, side. And then one last question. Use the properties of rigid motions to explain why triangle IJH is congruent to LJK. Doesn't have just to describe the rigid motion, but use the properties of it. Well, we know it's a rotation. We talked about that because of the markings, right? Well, how come if it's a rotation, then how do we know the triangles are congruent? Well, because the rotations preserve distance and angle measure, right? If the corresponding sides are all congruent, preserves. Okay, I was having trouble talking and writing at the same time. If the corresponding sides are congruent, that means the distance is preserved. And the corresponding angles are congruent, that means the angle measure is preserved. Then our triangles have to be congruent. I'm going to go like that. And angle measure. Okay. There we go.